for year 11 methods. We're going to look at the 2014 SAC I had due in class. So we'll just go over it and I'll give you some tips like as to how to approach SACs like these. Okay, so we've got liquid cools from the original temperature of 90 degrees. Okay, and it's given by this formula. Now let's interpret this formula because we've got 90. We got a base of 0.98 and to the power x. Now, because the base is less than 1, it makes sense. What's going on is that you're starting at an initial value of 90. So usually what the number is at the front of in front of the base is going to be your initial value. So you've got temperature that's cooling at 9 degrees and it's going down, and assuming it's going to go down to 0, basically. Okay. So you've got a decay scenario. So it's really important that you recognize if the base is greater than 1 and the index is obviously positive, then you've got a growth scenario. Here we've got a decay scenario. So it's decreasing by 2% every cycle, basically. Okay, so find the value of t when x equals 10. So this is just a plug-in exercise. So you're just subbing in 10 for x, 0.98 to the power of 10. And we want it to be standard decimal because there's 2 decimal places. So it's 73.54 degrees. Make sure you round properly. 73.54 degrees Celsius. Find the value of x when t equals 27. So they've given you a t value, you're just solving for x. So 27 equals this to the power of x. You're solving for x, basically. Interactive event solve for x. And we should get, so it's 2 decimal places, 59.59. So x equals 59.59, and always put your units. So x is in minutes. Okay. Next part, population of a large village at the beginning of 1800 was 240. The population increased so that after end periods, the population was given by this formula. Now, you can write P equals this, just so it makes sense. Now, what do you notice about 240 here and 240 there? It's, you remember the number in front of the power is always your initial value, okay? Usually, okay? When is that not the case? So if I have P equals 240 by 1.06 to the power n, and I've got plus 50, then your initial population won't be 240 only, it'll be 240 plus 50, okay? But in this case, because we don't have plus anything, or up-down translation, it's going to be 240, okay? So find the population at the beginning of 1820. Remember, our equation starts at 1800, so 1820 means n equals 20 years. So 20 years have passed, basically. So you're going to calculate 240, 1.06 to the power of 20. So that gives you, that's it, what that gives us. So 240, 1.06 to the power of 20. So the population, we're talking about population here, we're talking about people. So we always round up to the nearest whole number. Okay, so when we talk about population, it doesn't matter if it's point like 0.1, you always round up. So 770 people, because you can't have 769.71 people. Okay, it doesn't make sense unless we have a dismembered body, which we don't want. So it's 770 people. In which years the population first exceed 2,500? So you're going to sub in 2,500 for P, and you're solving for X, basically. So 20, we have X there. Interactive and solve. I get 40.217. So n equals 40.217. Now we have to interpret that. So please don't write that as the answer. Now, will 40 years suffice to give me a population of 2,500? Well, check. So if I were to sub in 40 into the equation for x. So 40, as you can see, it doesn't quite reach 2,500, and that makes sense because it says 40.217 years. So it won't happen in the 40th year. It will happen in the 41st year. Okay, so you have to interpret. So this is where rounding is important. So your final answer would be 1841. Okay, because 40 doesn't cut it. So it's the year 841. So now this is worth 2 marks. You're going to lose a mark if you wrote like 1840 because that's not correct. This is correct. Okay, so you got to pay attention to that. Question 3. We want exponential models. We're given table values, and we're just going to use the spreadsheet. Okay, so you have to use spreadsheet. You can do it with as little as 2 data points, but in this case, we've got like 5 data points. Okay, so just sub them all in. 3.1, 4.6, 12.7, 13.8, 19.6. And I'm just going to type in the y values. So 2.0771. You'll need to know this for the SAC. 2.9028, 17.693, 22.615, 82.805, 503, sorry. And then what you're going to do is you're going to go double check the values first. Yep, 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 yep. Okay, so I'm going to go calc regression, and we want AB exponential. Okay, we don't want exponential regression, we want AB exponential. So it says 2 decimal places, so y equals 1.04 times 1.25 to the power n or power x. So y equals 1.04 times 1.25 to the power x. For the second one, you just do the same thing. You just I'll get rid of this. Okay, I'll get rid of this, and you're going to type the values in. 1.6, 1.7, 1.8, 1.9, 1.9, go back, 2, then go up, 27.43, 26.79, 26.17, 25.56, and 24.96. Okay, I'm just going to go do the same thing. So calc regression, AB exponential. So it's 39.99. You have to round to 2 decimal places. So please work on your rounding if you're not familiar. The 9 goes to 10. So you essentially got 40.00 times 0.79 to the power x. Okay. So if you're not, like I said, if you're not familiar with rounding, if you're rounding 2 decimal places, make sure if it's a 9, you go up 1. So that comes a 10, that comes a 10, that comes a 10, so that comes a 40. So you're left with 40.00. Okay, so that's basically how you do part 3A B. For question 4, there are 2 species of insects living in the suburb, the Aspa bilba and the Catus pius. Okay, so I've got 2 graphs of the insects. So after January 1st means T equals 0 is January 1st. T equals 1 is 2nd of January. How many insects are alive on the 10th of January? Okay, so you gotta think about this carefully. If T0, if 1 is 0 and 2nd of January is 1, then the 10th, okay, so how many insects are alive on the 1st of January? So 1st of January, you're just subbing in T equals 0 on the 1st of January. So this is the initial, so you got to read the question really carefully. 1st of January means the initial amount. So Find initial amount by subbing in t equals 0. So initial means t equals 0. So the first one I can definitely find out. So for NA0, I know that this is linear. The y step is going to be 10,000 insects. For NC, for the other one, I get a value. If I sub in 0, I get, well, 2 to the power 0 is just 1. 1 times 3 is 3. 3 plus 8,000 is 8,003 insects. And so how many of each insects alive on the, so insects for, so what species? Number of Ishla bilba, and the other one is Cutis pius. Okay, so these are the amount of insects alive initially, and that happens to be January 1st. Okay, so it's how the time frame of the question works. State the day, 3 decimal places, and hang on, we've done, this is on the 1st of January, and for the 10th of January, we want NA, now because the 2nd January is T is 1, the 10th of January must be T9. So I'm just going to find what the value is on the 9th day. So if I sub in 9, I get for the first equation, oops, here, for the first equation, 1,000 to the 9. Okay, so 1900, not 19, well, 19,000 insects, and for the other one, 8,000 plus 3 times 2 to the power of 9. So it's 9536. Okay. So we've done that. And state the day and state the date corrected to 2 decimal places when there's the same number of insects alive. Okay. So you don't need to necessarily draw a graph for this. You just need to find when they're equal. Remember, when you try to find when these intersect, you just let that equal that. So y equals to y. So you're going to let, you can actually solve this simultaneously, basically. So I'm going to use the simultaneous tool on the CAS. So 1, 2, 4 plus 1000x, there you go, y equals that. And the other equation is y equals 8,000 plus 3 times 2 to the power x, is solving for xy. Okay, so the first solution is not what we're after because the x is negative, which doesn't make sense because t is between 0 and 15. We want the second solution basically. So the second solution is, let's see, it says state the day, which is 3 decimal places, and the date which insects with the same number of lives. So the to 3 decimal places, your t value would be 12.20 or 210, 12.210. So t will 12.210, and the date. Okay, so you've got to be really careful about what the date is. Okay, so remember how 9, when t equals 9, that's the 10th of January. Okay, so if it's 12, it's actually the 13th of January, but because it's 12.21, so if we want the same insects alive, we've actually got to go one day up, so we have to round up. So it won't be the 13th day, it'll be the 14th day. So it's January 14th of 2014. Okay. So that I know this is a bit confusing because we know the 1st of Jan is t equals 0, 2nd of Jan is t equals 1, 3rd of Jan is t equals 2, etc. So the t equals 12 must be the 13th of Jan, but because we're up 1, because it's not quite the 12th of 13th of Jan, it's actually the 14th of January to round up. So sketch the graph. An appropriate domain represents the number of insects alive. Okay. Label any insects rounding to 3 decimal places. Okay. So I'm going to try to graph this on the CAS calculator. Okay. Now you're going to have trouble graphing it automatically because if you look at the intercepts, they're quite big. So we're going to adjust our value. Now if you look at the x restrictions, it's between 0 to 15. So we've already got our x between 0 to 15. So I'm just going to go 0 to 20 maybe. But for the y, we're going to have to go really high. So 0 to, well, this is already 10,000 and we've got 8,000. So I don't know, we might want to do 30,000. Okay, I'm going to click OK and I'm just going to put these two graphs on the same axis. Okay, great. As we can see, if we get a quick scale, this is going to be quite nice. Okay, so I'm going to find an analysis resolve insect. It says to 3 decimal places. Okay, so all right, so let's graph. We need to graph. So the first graph's going to be linear. It's going to go, it's increasing. So our insect's at 10,000. So this will be number of insects, and this will be year, not year, day number, or time in days. So label the axis first. This is going to go up indefinitely. Not well. It's going to go up like a linear graph. So this will be 10,000. And then the second graph. So this will, and I need to label it. This is NAT. NAT. We do have to find the endpoint at 15. But I'll do that later. So the second graph will start at 8,000. So make sure it's roughly to scale. And it's going to look something like that. Okay, so the intersection point is 12.20 or 210, and then 22209, 61, I believe it's 618, it's 618, yep, 618. This is n b to power t, no, not to the t, it's function notation, and we've got to work out what the value is at 15 for either one of them. So just go xcal, ycal. So ycal, we want to find the y value at, okay, x equals 15. 15, 2500. Okay, so that's 15. And I'm going to just cut this short a bit because we have to have an endpoint. 15, 25,000. And for the other one, xcal, ycal. So I need to click the up down button to select the other graph. X value 15, y value would be 106,304. 106,304. Okay, so my graph would be like this. So 15, 106,304. So look, it is a bit tedious, but you've got to make sure you have your axis labeled, and a relatively good scale. I mean, I don't mean you physically need to draw a scale, just draw the important points. So here, intersection point and the end points. Okay, label the graphs. Just follow instructions. We'll go to the next question, question 5. They've given you equation, find P when H equals 0. That's very straightforward. I'll just go back to the main menu. I'll just clear everything. 75, 10 to the power. Now, girls, please be careful. Make sure you put brackets with the power, because you get it wrong otherwise. Times H. H is 0, so that's 75. This is around 2 decimal places, so please put 0. H is 10, so 710. 2.37 and 6 and when P equals 60. Okay, so they're giving you P and you're solving for H. 60 equals that. I'm just going to put a H in, X in, and I'm going to go interactive and solve. So 0.65. Okay, and P's in centimeters of H, centimeters Hg, and the P centimeters, H is height in kilometers, so that's in kilometers. Question 6, a radioactive substance is decaying according to this formula. When T equals 0, A equals 60.7. Now, A0 is always going to be your initial value. So, initial value is 60.7. So, we automatically know that that's 60.7, 2.71 kT. Now, we're just trying to find the value of, so we've got A0, we're just trying to find that value of K. So, sub in the coordinates when A equals 5, T equals 6. So go interactive and solve for K. Okay, again, brackets, please. 6 times X, interactive and solve. So K equals negative 0.4, because it says 1 decimal place. Okay, so got so we know A0 equals 60.7 and K equals negative 0.4. Alright, so just realize that whenever you have a formula like this, the A0 is always your initial value, okay, or the A value is always your initial value. Question 7, we've got mice, they've given you an equation for it. So it is since the 1st of October, how many mice are in the 3rd of October? So the 1st of October is 0, 2nd of October is 1, 3rd of October is 2. Okay, so you got to get the dates right. 300, so I'm just subbing in 2 to the equation to power 2. So how many mice are there? So nearest mouse would be 469 mice. Okay. On which day number would exceed 10,000? So you just go 10,000. So you're subbing in 10,000 for M equals that to the power X. Interactive and solve for X. Okay, which day number? So it's day, it's not 50, so we've got a value of T equals 15.71. So essentially it's on the 16th, not 16th, but you round it to 16. Okay, you round up to 16, so it's on the 16th day. So let's go back to our system. So day 1 is it's the 1st of October is day 0, 2nd of October is t equals 1, 3rd of October is t equals 2. So if second of October is t equals 1, then t equals 16 would would be the 17th of October. Okay, so it's really important. Spend some time. I know it's a bit confusing because I get mixed up with this as well, but spend some time on working out like the correct day and how the date system works. On which day we'll exceed 1 million. So I'm just going to add a few more zeros. So make sure we have three. Yep. On which day would it exceed 1 million? So 36. Right. So we'll look at the month of October. I think October has 31 days. So I'm going to check. I'm not sure myself. October has 31 days. Okay, so 1st of October, 0. So there's 30 days. 30 days. So what? 37 days. Okay, because if we round up 36.35, it's on the 37th day. So if 30 days have passed, it'll be the 7th of not October, but November. Okay, so the answer will be 7th of November. Question 8, we've got a model. There were initially 20,000, so again, NO will be your initial value, so 20,000 will be your NO. So NO equals 20,000. After 10 years, there are 704 people that had the disease, and it's known that the disease is increasing by 20% each year. So if you're increasing by 20%, your base must be 1.2. So your A value would be 1.2. Because if you're increasing something by 20%, you go 1 plus 0.2. Okay. So we're trying to solve for K. So N equals 20,000 times 1.2 to the power KT. So when after 10 years, so when the population is 704, we've got a t value of 10 and times k, so we try and solve it. So 704 equals 20,000 times 12, oh not 12, 1.2, to the power of brackets 10x, because x represents k, interactive and solve for k, for x. So, oh sorry, this is people decreasing. So let's go back. Decreases by 20%. It's not 1.2. It's 0.8. That's 0.8. So that should be 0.8. That should be 0.8. Yeah. So 0.8. 0.8. So let's go back here. 0.8. So it should be 1.50. So k equals 1.50. So we want to sketch the graph showing project features. So we've got this, and this is 1.50. Or I can be more precise and go 1.998009. So you're going to graph this on a CAS, and hopefully this shows us something. Okay, great. So it makes sense. So what's happening here is that we've got a graph and it's decaying, and we're going to have, this is, so on the y-axis we've got population, and on this axis, we've got T, which is years. Okay, and what's happening here is you've got a graph. The initial population is to 20,000, and it's slowly decreasing, and you have an asymptote at P equals 0, basically. Okay, you have asymptote. So what I'm after is this point, and it's always good to have a second point. So you might want to show that the population after 10 years, so after 10 years might be here. We've got a data point. After 10 years, there's 704 people. So I've shown my asymptote. I've put an equation of asymptote. I've labeled my axis. I've shown the start point, and I've shown the second point. So that should be good to go. So hopefully that helps. I've gone through the SAC. There are some things that you do need to pick up, so make sure you go over them if you're not really sure. So